Today's problem is safe states. Difficulty is medium. Let's see. This is a fairly common question regarding directed graphs. Given a directed graph with V vertices numbered from 0 to V minus 1 and E directed edges represented as a 2D array edges, where each element in edges is a two-element integer array. Let's call it U, V, and it represents a directed edge from vertex U to vertex V. A vertex with no outgoing edges is called a terminal node, and a vertex is considered safe if every path starting from it eventually reaches a terminal node. So be clear about what they're talking about. They're not talking about if you start from a vertex, it's safe if you could reach a terminal node. It's safe if you have to reach a terminal node. Every path reaches a terminal node. Okay. Return an array containing all the safe vertices of the graph in ascending order. Okay. We might look at this in a little more detail. Well, actually, let's just do a quick look at it here. The terminal nodes, that is, the nodes that have no outgoing edges, would be 0 and 4. All right. Now, let's look at the other nodes. All right. From 1, we could go to 0. So that's a good path. Or we could go to 2. From 2, we have to go to 3. From 3, we have to go to 4. All right. That's also a terminal node. So that's safe. Also, from 1, we could go to 3. From 3, we have to go to 4. That's a terminal node. Or from 1, we could go to 4. So 1 is safe. It always winds up at a terminal node. What about 2? From 2, we have to go to 3, and then to 4. From 3, we have to go to 4, and 4 is already a terminal node. So all of those nodes are safe. Now, in this one, the only safe node is 0, sitting out here by itself. It's a terminal node. It's the only terminal node. And yeah, so just to be clear about this, I've just set up a pen here. I'm going to add another node here. Here's node 4. Okay, and 3 goes to 4. Well, now 4 is a terminal node. But let's look at 1 or 2. The thing is, from 1, is 1 a safe node? Well, we could go from 1 to 2 to 3 to 4. That's it, right? Well, not really, because we could go from 1 to 2 to 3 to 2 to 3. You know, just get stuck in that. So it doesn't have to reach a terminal node. So that's no good. That is not a safe node. And really, that's the way the algorithm works. Is we're going to take each vertex and do a depth first search on it and see if we can find a cycle. Okay, if we find a cycle, then the node under consideration is not a safe node. Okay, let's get rid of that. If you look back up here at this one, there are no cycles in this graph at all. Because there are no cycles, then every node is a safe node. Okay. Constraints: number of vertices between 1 and 10 to the 5th, 100,000. Inclusive number of edges is between 0 and 100,000. Inclusive edges. The vertices in the edges array will be between 0 greater than or equal to 0 and less than the number of vertices. In other words, they will all be valid. That's a good thing to know. And if you're not told that, then you should inquire, can I assume that all of the vertices in the edges array are valid? There's really no reason to give somebody a problem where you're going to have. No, I mean, I take it back. I take it back. If you were doing a real world solution to something, you would validate the vertices. But okay, let's just go with the fact that in this problem, they're all valid. Expected complexity, time complexity V plus E. Yeah, we're gonna visit each of the we're gonna visit each of the vertices and potentially traverse all of the edges. So V plus E, auxiliary space O of V. The auxiliary space would be, because they're giving us the edges in a format that we can't really use, and so we have to put them into a different format. I don't think we need. Well, actually, I take that back, because we are doing a recursive depth first search, so we need space for the stack as well. But we do have to get these edges out of this format that they give us here, which is just, well, we have an edge from 1 to 0 and 1 to 2 and 1 to 3 and 1 to 4, etc. So you can't really use something like that. I mean, if you want to know, like, well, how many edges are adjacent to vertex 4, you would have to scan through the whole array to see that there aren't any, that kind of thing. Actually, in LeetCode, I've seen problems there where they'll give you a graph in this format, a 2D int array, but the way it works over there is each index in the array is an array of vertices adjacent to, what am I trying to say? So like for this one, let me grab the pen again. You would have an array like this. It starts out, there are no vertices from 0. So at index 0, you have an empty array. Okay, at index 1, you have 0, 2, 3, 4. Okay, at index 2, you have 3. Now you can use that directly. It's like an adjacency, it's an adjacency, that's not an adjacency matrix, I shouldn't say that, but you can use that as an adjacency list. You can say, well, how many vertices can I get to? Whoa, how many vertices can I get to from vertex 2? And then just look here, and you can get it. All right, with this one, with this format, you can't get it. All right. What else before we get started here? Auxiliary space, topic tags, depth first search, breadth first search. I guess you could do this with a breadth first search. To me, a depth first search makes more sense. But all right, let's look at this. Safe nodes. Okay, graph. Yeah. In problems like this, I like to create a graph class. Now, you don't have to create a graph class. Really, what we need here is we need adjacency lists. We need an adjacency list. You could create, a list of lists like this, right in this method. But if you're trying to get hired as an object-oriented programmer, it makes more sense to me to demonstrate your ability to create and use appropriate classes. So, what we're going to do here is to create a directed graph class. We pass into the constructor the number of vertices and the edges array. We store the number of vertices, create an array list, and put array lists in the array list. Put empty array lists in the array list. The number of empty array lists that we put in there corresponds to the number of vertices. Each one of those array lists will represent the vertices that are adjacent to the vertex at that index. Iterate through the edges array, adding edges. How do we add edges? Well, we add the vertex to the corresponding array list. Let's see, VW. How did I look at this? This looks wrong. We don't want to add V to W. We want to add we want to add it this way. We want to add W to V. Okay, let's see. And then we have a method down here. Now the adjacency list is private here, but we have a method where you can pass in a vertex and get the adjacency list for that vertex. Okay, that's it. That's the directed graph class. States. We want a state array. There are 3 states that a vertex can be in. They all start out as unvisited. So if we just create this states array, it gets initialized to 0. Everything is 0. Everything is unvisited. All right. First time we visit a vertex as part of a depth first search, we mark it as visiting. Now, if we get back to the visiting array, if we get back to if we get back to a node that is in visiting state, that means we've found a cycle, and so the vertex under consideration cannot be a safe node. Okay, the final state that it can be in is safe. Here's our list of safe nodes. And for each vertex, we're going to run a depth first search. The way we've set the depth first search up is if it returns true, the node is a safe node. So we add it to the safe nodes, sort it as requested, right? We need to return in ascending order and then return it. All right, let's look at the depth first search. Maybe it would help to... can we see everything here at the same time is the question. Let me scoot that over a little bit. Pretty close. Okay. All right. So again, we're looking for cycles. If there is no cycle, then the node is safe. And what we would do is, here let's start out with vertex 0, and we'll set it to, first of all, we'll come in here. Is it in state 1? And it isn't actually. When the first time we look at it, it's in state 0. Is it in state 2? No. Well then, in that case, we're going to set it to visiting. Now we look at all the adjacent nodes to 0. There are no nodes adjacent to 0. So we'll just drop through that and we set the state of node, or I'm sorry, vertex, yeah, node 0 to 2. It's safe, and we return true. So that's fine. Next node is 1. Okay. Nodes adjacent to 1. Well, first of all, we're going to set this to, it comes in as 0, so it's not 1, it's not 2, but we will mark it as visiting. Okay. Now, for everything that's adjacent to 1, well, 0 is adjacent to 1, but we've already marked it as safe. So that's fine. 0 is good. Next thing we got to look at is 2. 2 is adjacent to 1. All right, so we'll put that in there, and we're going to set the state to visiting. Now we have to do a depth first search on 2. 2, well, from 2 we can get to 3. All right, so we'll put 3 there. 3 we're visiting. From 3 we can get to 4, so we'll put 4 in there. When we call it with 4, what we're going to find is 4 has no adjacent node. So 4 is safe, right? Because 4 is safe, when we unwind the recursion back to 3, the only adjacent node to 3 is 4, and 4 is safe. So in that case, 3 has got to be safe. Now we'll unwind it back to 2. The only node adjacent to 2 is 3. So if 3 is safe, then 2 is safe. Okay, now we're back to 1. We're not quite done with 1 yet. We still have to check the adjacency from 1 to 3, but 3 is already safe. From 1 to 4, 4 is already safe. So then 1 becomes safe. So everything there is safe. And let's take a quick look at this one down here. 0. All right, so we'll start with 0. And 0 is going to be a safe node. It has nothing adjacent. 1. So if we come into 1, and we'll set 1 to visiting. Okay? And it has one node that's adjacent to it, and that would be 2. Okay, so we'll set 2 to visiting. 2 has one adjacent node, and that is 3. Okay, so we'll set 3 to visiting. 3 has one adjacent node, and that is 2. Now 2 is already visiting. So now we are in this situation right here. Okay. We are visiting a node that is already marked as visiting. So so when we unwind the recursion here back to 1, we're going to find that 1 is not a safe node, and of course 2 and 3 are not going to be safe nodes either. All right, that's it. Let's delete everything there and run this. Let's see. All right, I gotta scroll down. Actually, let me, because I changed a couple of things. Let me do a sanity check on that. Okay. Now we'll try and run it. Okay. Pretty common directed graph problem. So yeah, I can't think of anything else to add to it. Anyway, go ahead and like the video if you liked it, or if you didn't like it and you're feeling generous, you could like it anyway. You can subscribe to the channel, and we'll see you next time.